8.2, polar area or polar integration, if you will, which a lot of it deals with not polar accumulation, but we are going to be finding a lot of the beautiful curves that we talked about on Friday, a lot of the areas of those curves. All right, so we're going to be finding polar area in a slightly different manner than we found rectangular area. Rectangular area was from left to right on the x-axis, height minus width. The way that we're going to find polar area is going to deal more with rotation out of the pole. So what we need to do is review what the formula for the area of a sector is. All right. So let's say we have this function r in red here that's traced out from theta equals alpha to theta equals beta. Okay. I want to find the area of the green region there. We're not going to be finding, the area from left to right. So what we're going to be doing is we're going to be partitioning this up into infinitely thin theta pieces. And on each of those theta pieces, if you make them small enough, the curve starts to represent the area of a circle, right? And why is that important? Because if it were circular, purely circular, and not curvy, what's that? Is it on freeze? Okay. Thank you. I did the double thing real quick. Freeze, unfreeze. Or unfreeze, freeze. If I could take my d thetas to be small enough, like we did for the delta x, if d theta is small enough, then this curve starts to simulate more and more the area of a circular sector. Okay, so let's review that. If we have a circle, like a pizza, and we cut out a slice of pizza, this is called the sector of a circle. And in pre-cal, we derive the formula for finding the area of that sector for an angle theta in radians. Do y'all remember what it was? The area was equal to, it's equal to 1/2 r squared theta. We did it as a proportion. We did part to whole. We did theta is to 2 pi as the a is 2 pi r squared. And then you solve. Okay, so it's not that difficult to come up with. But that gives you the formula of the area of a sector in terms of theta. So what we're going to do then is we're going to make these curved regions infinitely small angle-wise so that the central angle is d theta, so that each of these will simulate an area of a sector of a circle and not a curve in general. And so to find the area of the whole thing, it comes down to the idea of, again, taking the sum, the infinite sum of the infinitely small pieces from theta equals alpha to theta equals beta of 1/2 r squared, and then the theta becomes d theta because it's infinitely thin. So this is the formula for polar area. Now, of course, because the 1/2 is a constant multiple, where can it go? It can go out front. So you do need to memorize this formula. This gives you the formula for polar area from theta equals alpha to theta equals beta. It's 1/2 r squared d theta. Of course, an r is a function of theta. Right? Questions on that? Memorize it. 1/2 r squared d theta. 1/2 r squared d theta. Let's try it out. Find the area bounded by the graph of r equals 2 plus 2 sine of theta. So what can y'all tell me about this graph? I'm going to work everything, by the way, today in monochrome, simply because on the AP exam, you're going to have a pencil. All right? It's a cardioid. Good. With what type of symmetry? Y-axis symmetry. So this is where it's kind of especially useful to figure out how it traces out. So again, if you just hit the quadrantial angle starting at theta equals 0, what's our first radius point? When theta is 0, we get 2. Okay, so the radius is 2. As we rotate up to pi halves, sine of pi halves is 1, so we end up with 4. When you go over to pi, sine of pi is back to 0, so we're 2 units in the other direction. 3 pi halves, you get -1, so that's where you get 0. So there's your polar 0. And then it finishes up. So to trace out, it starts like this, and then it bounces out of the pole at 3 pi halves. And then it traces out once from 0 to 2 pi. We're trying to find the area of that graph. Okay? We want to find the area of this cardioid. So how are we going to do that? Well, the simplest way is to pull out the formula for polar area. The area is equal to what? 1/2 the integral from alpha to beta of r squared d theta. Good. So let's see. Do we know what our equation is for r? Yeah, it's 2 plus 2 sine theta. So if you want to start plugging in, it's 1/2 the integral of r squared d theta. And r was handed to us. It's 2 plus 2 sine of theta. So that's good. We just need to figure out the intervals of integration, which are your angles. Well, there's many different ways to do this. So we trace it out from what? 0 to 2 pi. So if you think about your radiuses, if you start at 0, as you rotate, here's what your radiuses are doing. Okay, and then I said I was going to do monochrome, but this just looks so good. And then we finish up right there at 2 pi. So the easiest way to do it is to go straight from 0 to 2 pi. Yeah. No, they both trace out. All the cardioids trace out from 0 to 2 pi. The sine cosine just determines if it has y-axis or x-axis symmetry. The ones that trace out from 0 to pi, remember there were 2 of them. Oh, look, I got a YouTube request. Nice. The ones that trace out from 0 to pi are your off-centered circles, like 3 cosine of theta or 4 sine of theta, and, of course, the odd-pedaled rose curves, like 4 sine of 3 theta or 6 cosine of 7 theta. Everything else traces out from 0 to 2 pi for the most part. All right, so here's the setup. So you could do it like this, and this works great. This could be perhaps a multiple choice question where it says which of the following gives the area of the polar region. So that certainly will work. But a lot of the times they use symmetry. All right? So notice this thing has y-axis symmetry. So with symmetry, you could set it up a different way. You could double it. It would be 1/2 the integral from something to something. If you just find like the right half of it, which is typically what we do as opposed to the left half. If I start at 0, though, and I go all the way to pi halves, that's only going to give me this part of it. So you could actually back up how far? Back up 90 degrees or how many radians? Yeah, go to negative pi halves. So if you went from negative pi halves up to pi halves, that's still a span of pi. And so what that does is it backs it up in negative land towards 3 pi halves. Remember, we hit there with 3 pi halves going forward, but it's coterminal with negative pi halves. So now if you integrate from negative pi halves to pi halves, you're going to get that right side of it. You can double it. Now, why would we be interested possibly in using symmetry? Because the formula always has a what in front? A 1/2. What's twice 1/2 now? 1. And so if you see a multiple choice question and it looks like it's using symmetry because there's no 1/2, that's probably what's happening. All right? But really, if you're doing it by hand, any one of them could do it. There's lots of ways to do it. You could just integrate from what? Pi halves to 3 pi halves. And that would give you the left side of it. And then you could double it as well. So lots of different ways to do this. You can go from negative 2 pi to 0 if you want. Because of the coterminal nature of all these angles, there's many different intervals that work. All right, so with that said, let's go ahead and evaluate it. Now, I'm going to evaluate it one time by hand, and then after this, I'm going to say if it's a non-calculator question, you're going to evaluate it the same way. If it's a calculator question, you're picking up the calculator at this point in radian mode, and you're evaluating it. But these can show up on non-calculator questions, okay? We could do this one. This one uses symmetry, which is fine. But you know what? I would prefer to have a 0 in my interval of integration rather than use symmetry. The 1/2 is not going to be an obstacle to me. I just wanted to show you that it's possible that we could use symmetry. And sometimes it's advantageous to do so. But in this case, having a 0, I think, is easier. All right, so I just got to keep track of my 1/2 out there. Now, if I'm going to integrate this by hand, you will have to expand things. All right, so square multiply double square, you get 4 plus 4 sine of theta, and then you square it and you get plus 4 sine squared of theta. Now, if you do that, you can actually now distribute the 1/2. Oh, 2 times 2 is 4. 4 doubles is 8. Thank you. I made a careless mistake. Appreciate it. Square, multiply, double, square. I square, multiply, and then double. Square, multiply, double, square. So now if you want to distribute the 1/2, it's your prerogative. I think that would be kind of nice. Because now you end up with 2 plus 4 sine of theta plus 2 sine squared of theta. Now notice that the first two terms, they're ready to go. We can integrate both of those pretty easily with respect to theta. How are we going to integrate sine squared, though? By parts, not a bad idea. There's actually, by parts, that might get a little bit ugly. This one you're going to actually use an identity, okay? So here's where the power-reducing identities are customarily used. Sine squared of theta is 1/2, 1 minus cosine of 2 theta, and cosine squared of theta, which could show up, is 1/2, 1 plus cosine of 2 theta. So these show up quite a bit in polar area because of the formula r squared, and a lot of times we have sine and cosine. So when you're doing these by hand, they are pretty labor intensive. So I would recommend perhaps just integrating everything at one time if you have to do so. So now I'm going to rewrite that last term. Well, look what happens if I replace sine squared with 1/2 quantity, 1 minus cosine of 2 theta. The 2 in the front of the sine squared and the 1/2 from the formula do what? They cancel, and I'm left with plus. So I could just write it as then plus 1 minus cosine of 2 theta. There's nothing to distribute other than a positive 1. The 1/2 divides out with the 2. And now, if you wanted, you could even simplify one more time, because the 2 and the 1 can join forces and become 3. So 3 plus 4 sine of theta minus cosine of 2 theta. All right, now we're finally ready to integrate by hand. So here we go. The 3 becomes a what with respect to theta? 3 theta, good. Plus the 4 goes for the right, and sine becomes negative cosine. So it becomes minus 4 cosine of theta. And then here I have an inside function now from the double angle identity of a 2, an unwanted 2, so I have to have a correction of a 1/2. And then the antiderivative cosine is positive sine. So it's minus 1/2 sine of 2 theta. And then I will evaluate it from 0 to 2 pi. And now to plug in. For theta, we get 3 times 2 is 6 pi minus, what's cosine of 2 theta? Or 2 pi, sorry. Cosine of 2 pi? 1. So we're left with minus 4 minus, what's sine of 4 pi? Well, that's the same as sine of 2 pi, 0. Yeah, so minus 0. So there's plugging in the top, in parentheses, minus, parentheses, plug in the bottom. 0 times 3 is 0. Minus cosine of 0 is 1, so we're left with minus 4. And then sine of 0 is still 0. So with all that, we end up with 6 pi minus 4 plus 4. We end up with 6 pi. And there's the answer. And there's a lot of different ways to come up with 6 pi. As long as the interval is correct, the coterminal nature of all these angles will still get you 6 pi. So notice, if it's a non-calculator, it's a lot of work, but it will require the power-reducing identity. So a lot of times, what you have to do instead of evaluating it on a non-calculator is you have to just identify the setup, and your answer choices will be setups. Otherwise, more than likely, it's going to be a calculator question. So let's see what that would look like. We'll type in both versions and see if we don't get the decimal equivalent of 2 pi. Now, if you are going to be sketching this, let's say it is a calculator question, you're probably going to be in polar mode, right? You're probably going to sketch it and see what the graph looks like. So let's go ahead and give that a whirl. Type it in. The function was 2 plus 2 sine of theta. And if you hit zoom 6, there's the graph that we had. All right, so nice. Now you go to the home screen. Let's type in the one that we actually evaluated, this one here in the light blue. So if I type that in, I'm going to type it in as 0.5, math 9, and I'm still in polar mode, I'm going to go from 0 to 2 pi. And now when I recall my function, it's r squared. Where's my function? Alpha trace. When you're in polar mode and you hit alpha trace, you get your r's. So I had mine in r1 squared. Pretty nice with respect to theta. So you can keep it in polar mode. You get that, and you get 18.849, which should be 6 pi. And it is. Pretty sweet. All right, let's type in the other one that used the symmetry. This one right here, negative pi halves to pi halves. Should be the same. This time there was nothing out front, so it's just math 9, negative pi halves to pi halves. Oops. And our function is still r squared, so it's still alpha trace number 1 squared d theta. And I hit graph. Nice. You get the same thing. If I recall it, and if I double it instead of negative pi halves to pi halves, if I would have gone from pi halves down here to 3 pi halves, that would be like what I mentioned, finding the left-hand side of it and then doubling it. You get the same thing, see? So there's lots of different equivalent intervals. The key is for you to at least find one interval that works and then go to the calculator with the 3-decimal approximation, or if it's one of those ones where you have to actually evaluate it, you're going to need the power reducing identity. All right, any questions on that one? 1/2 r squared d theta. Okay, so example 2. We're not always going to be finding the whole area of the entire region. In this case, it says find the area of one petal of r equals 2 sine of 3 theta. So what can you tell me about this function without a calculator? 3 petals. Good. 3 petals. What's the petal length of each of them? Okay, the petal width or length is 2. And it traces out once from 0 to what? Pi. Good. The odd number of petals, you're going to see that number from 0 to pi. So if you want to find one petal, again, let's kind of treat it like it's a non-calculator. Figure out how it traces out. At 0, when theta is 0, what's sine of 0? 0. So it starts at the pole. There's your first value. It starts at the pole, and then what about at pi halves? Ooh, this one's going to be hard, right? Because it looks like it's going to start at the pole. Now, what this means then, if it starts at the pole, it's going to trace out, boom. It's going to go out and come back. So what you want to do, there's one petal, right? The other one's going to probably be over here, boom. The next one's over there, boom. Or actually, maybe it doesn't look like that. It has to be symmetric. So it looks like this and like that. But the same. There we go. There we go. It looks better. So here's what you want to do. Just realize that for one petal, you want to integrate between consecutive polar zeros. Would you agree? Between any two consecutive polar zeros, you're going to have one loop. Well, if I know I started one at 0, I just need to find the very next one. So here's in general how you can do it. How do we find polar zeros? We said r equal to 0. Yeah. So let's see. 2 sine of 3 theta equals 0. Divide everything through by 2. You get sine of 3 theta equals 0. And then here's where we have to kind of think about what happens to sine of 3 theta. That's compressing the graph of sine horizontally by a factor of 3. That's making the period 3 times narrower. So solve it for sine. Where does sine normally equal 0 if it were just sine of theta? At 0 and 2 pi and pi. Let's throw that one in there. Don't forget pi. So 0, pi, 2 pi, then 3 pi, 4 pi, so on and so forth. Those, though, are not equal to theta. Those are each equal to what? 3 theta. It's almost like I took the inverse sine of both sides and then found the first few positive solutions. Well, now all I have to do to solve for theta is divide everything through by 3. So that means theta equals 0, theta equals pi thirds, and then the next one would be at 2 pi thirds. So what I'm doing is I'm finding consecutive zeros. So really now I can integrate from 0 to pi thirds. Or I can integrate from pi thirds to 2 pi thirds. Or the next one I guess would be at pi, right? So whenever you can get 0 involved, that's nice. So this thing traces out from 0, and then boom, hits 0 again at pi thirds. So let's go ahead and set it up. The area is going to be 1/2 the integral between consecutive zeros, which would be from 0 to pi thirds to 2 pi thirds, 2 pi thirds to pi, whatever, of r squared d theta, and then r is 2 sine of 3 theta. So there's the setup. Let's go ahead and simplify now. I have to square the 2, right? So what's 2 squared? 4, and when you pull it out front times the half, that turns it into a what? A 2. So the simplified integral would be 2, 0 to pi thirds of sine squared of 3 theta d theta. This could be your multiple choice answer. On a non-calculator, they realize what's involved in using the power reducing identity. So they might just say, which of the following gives you the integral for the area of one petal? And that would be your answer. If you had to go on and find it without a calculator, you would use the power reducing identity. Okay? But in this case, let's just go to the calculator. We would type it in, 2 math 9 from 0 to pi thirds. Now in this case, I haven't typed my function into R1. So I'm not going to just refer to R1. I'll just type it in as sine of 3 theta. And remember your calculator, when you close the angle and then square it, it acknowledges that as squaring the whole function, and then d theta. So whatever you're more comfortable doing. That should look pretty much exactly like what you have written on your paper, and then you get the answer, which is 1.047. That's one petal. What if it had asked for the area of the entire rose curve? Multiply by 3. So even if it had said that, you might still want to then opt to find one petal and then just triple it. Okay, or if it was an even, you would find one petal and then, make sure that you know that there's twice as many petals that you would see. All right, questions on numbers 1 or 2? You got the power reducing identities memorized? You got the formula for polar area memorized? If you can do that, you pretty much have it down. Now, it does get a little bit more interesting. As you'll see after lunch, we'll do like inside one function and outside another. So we'll be finding area between two. And sometimes that can get kind of fun and interesting. We may not finish today after lunch. If we don't, we'll probably do example 7 tomorrow just to finish it up and look at kind of like a sample free response type question and then move on to sequences and series. But at this point, you have everything you really need. It's just a matter of practicing and finding points of intersection between polar curves. We haven't done that yet, but I'll save that for after lunch. All right. We'll stop right there then because it's a good stopping point.